Okay, next speaker is Chen. He's speaking about kernels.
Okay. Yeah. Hello, everybody. Today I'm going to talk about deep neural tangent kernel and the Laplace kernel have the same RKHS and another project. Okay. This is the word population iClear 21. So let's have a quick review of what's a kernel. K from E times E to R is a kernel if it is symmetric, and the Gram matrix is positive semi-definite for any x1 through xn. And for each kernel, we have associated reproducing kernel Hilbert space, and let's also have a quick review. An RKHS on E is a Hilbert space with a function k from E times E to R, which is called a reproducing kernel, and it must enjoy the reproducing property. First, we require that k sub x, it is k dot comma x. It must be in the Hilbert space, and the reproducing property is that for any function in the Hilbert space, f of x must be equal to the inner product between f and k sub x. And there is a theorem for any kernel k. There is this uniquely determined RKHS denoted by h sub k of E, admitting the reproducing kernel k on E. Okay, and what's a neural tangent kernel? People found that a gradient flow on normally initialized, fully connected, infinitely wide neural network is equivalent to kernel regression with respect to the NTK. And we use n sub k to denote the k plus 1 layer ReLU NTK on the unit sphere. And nk can be is given by the following recursive relation. So we relate nk to some function kappa 0, kappa 1, and nk minus 1, where kappa 0 and kappa 1 are two functions, and kappa 1 to the k is the kth iterate of kappa 1. Okay. My first result is the RKHS of the ReLU NTK is actually equal to the RKHS of the Laplace kernel if they are viewed as a sets. So to be precise, we let h of lap and h sub nk be the RKHS associated with the Laplace kernel, which is e to the minus c norm of x minus y, and ntk on the unit sphere. Then the two spaces include the same set of functions. Note that this equation holds no matter how many layers you have. So even if you have many layers, but the RKHS of the neural tangent kernel, ReLU NTK will not grow with more layers. And since an RKHS characterizes the expressive power of a kernel to some extent, this is actually a negative result for the kernel regime of neural nets. Proof technique. So I analyzed the decay rate of the power series coefficients around 0 of the kernels using complex analysis, and the decay rate is determined by the asymptotic order around the closest singularities. Okay, and the second result. In the second result is about smoothness and the size of the RKHS. Here I consider the exponential power kernel, which is given by exponential to the minus the norm of x minus y to the gamma over sigma. And I consider the exponential power kernel on the unit sphere and the entire space. And note that the exponential power kernel is a generalization of the Laplace kernel if gamma equals 1. And here I have an illustration of the kernel for different gamma values. We can see that if gamma is 1, which is the blue curve, and if gamma is 1/2, it is the red curve, and if gamma is 1/3, it is the green curve. We can see that if gamma is smaller, then the kernel is more non-smooth. And the theorem tells us that if we have a smaller gamma, then the RKHS is actually larger, no matter you are on the entire space or on the unit sphere. And technique, so we want to prove the inclusion of RKHS. It suffices to prove that the difference of the two kernels is positive definite. And we can prove this using inverse Laplace transform, which can be obtained by contour integration. Okay, so these are the two main results of my first project here. And the second one. The second one is about feature engineering. It was published on ESA 21. Okay, so let me show the main results first. Let P0 and P1 be two distributions on the product space of V1 through Vn. And A is a subset of 1 to n. And we write a partial product space V capital A is the product of VA for A in capital A. And we denote the marginal distribution on V sub capital A by P0A and P1A. And the first result is the hardest result. I show that there is no n to the 1 over poly log n approximation algorithm for the following maximization problem unless the exponential time hypothesis fails. The exponential time hypothesis says that 3 set cannot be solved in sub-exponential time in the worst case. And the maximization problem, which is hard, is the following. We want to maximize over all size k subset of n. And we want to maximize the total variation distance between P1A times P0A and P0A times P1A. This is hard. Without any assumption, it is hard in general. But if P0 and P1 are factorizable, that means they can be expressed as product of marginal distributions on each VI, then this function is monotone and submodular. Submodular means FA plus FB is greater than FA intersection B plus FA union B. Then there is this a polynomial time 1 minus 1 over E approximation algorithm. So this is the tractability result. However, you may wonder, why do we need to care about this function? So why we are interested in this kind of function? Well, let me show you why we care about that. It actually arises in when we solve a feature selection problem. And we believe that this result can be of independent interest to statisticians. Okay, we consider a classification task, and we are given n categorical features and a binary label column. We use xi to denote the value of the ith feature column, and the c be the binary label. Vi is the vocabulary. Then we model data set as a distribution. So that means x1 through xn, comma c follows the distribution d. Let's see this example. In this example, we have two feature columns, which is country and the language. And we have a label, binary label. And the data set is very small. It only has 2 rows. The first is Scotland and English, and the second row is Mexico and Spanish. Then x1, x2, c follow distribution. It is Scotland, English 1 with probably 1/2. And it is Mexico, Spanish 0 with probably 1/2. And the vocabulary of the first feature column is Scotland and Mexico, and the vocabulary of the second column is English and Spanish. And we want to select a subset of feature columns. And we need to quantify how good the selected feature columns are, right? So let's consider a very simple model here. We consider the score function sigma that assigns a score in 0 and 1 to each value of the selected feature columns. For example, if A, the selected feature column, only contains the country feature in the previous example, and we can assign Scotland, we can assign 1/3 to Scotland and assign 1/2 to Mexico. Then given a threshold between, yeah, thank you. Given a threshold between 0 and 1, we predict 1 if sigma is greater than the threshold and predict 0 otherwise. Then we can get a positive and true and false positive rate. Then we vary tau from 0 to 1, we get a curve. The AUC, the area under the curve measure is the area under this curve. It measures the performance of sigma. And because this measure depends on the selection of sigma, we can see that the optimal AUC, which is the AUC of the optimal score function. And we find that AUC is actually equal to a linear function of the total variation distance here we just consider. Then our results give the following. So there's no approximation algorithm for this maximization problem unless the exponential time hypothesis fails. And under the naive Bayes assumption, there is a polynomial time 1 minus 1 over e approximation to this maximization problem. So this is our the main result of my second project here. Yeah, thank you so much.
Any questions? Okay. Yeah. So we want the next speaker. That's it.